So next up we've got Modernizing Legacy, wrapping a 25-plus year Computational Fluid Dynamics codebase by Duy. I'd like to welcome you.
Thank you, guys. And thanks a lot for tuning in. My name is Duy, and I'm from CSIRO. Today, my talk is about taking something old. A backstory is I have my boss actually wrote the Computational Fluid Dynamics. I will talk about that later, what is CFD mean, but he wrote that code base as a model back in the 90s. And then he took that with him, so he's from Germany, and took that with him from German to UK to America, and then now in Australia here. So a lot of people using his code. And then summing up that we want to build a data system that run in Python environment, and we want to use that code. So that's why I'm here. I try to give a bit of light in how could I actually take that and then run in the new environment. My background is totally in physics, and I only tuning to work on Python. It's just only little less than 2 years ago. So please be mindful that if I using sometimes wrong terminologies, and I want to start up with the motivation behind the whole, what is the nice, beautiful picture up there. It's my work is on the environment space. So I work in water quality, and I try to track and write model about monitoring and forecasting water quality. And water quality, water, you know that it is kind of interconnected. But it is challenging that with the climate change and then increasing of the population, it is challenging. And a lot of people are at risk of illness from poor water quality. And of course, we need to build a system that could be monitoring and forecasting as well of inland and coastal water. And how we do that in CSIRO. So I'm introducing a concept. We call that aquawatch. Aqua is aquatics, and what is the watching. And how we do that? So we use kind of a combination from ground, so a lot of sensor on the ground, and grab sampling. We send someone to the lake, to the river, and grab the sample. And we combine that with satellite data. You know that satellite up there, it could take the image with more wider of the space. So it means that if you combine all of them together, you would have the advance of both temporal and spatial resolution. You could scale it up. And to build that, we need an analytic hub system, and we need an ecosystem of modeling. First is the data system. So this is the cloud-based solution for water quality monitoring and forecasting. So you can see that it have 3 components there. So you have the data ingestion component. So you have all the ingestion from satellite and sensor network, and an open data library that collect and deliver raw data. And then it all go into an analytic and data storage. And it is the hub and platform that process and manage a large data sets for analysis. And of course, you need to deliver that to the end user. And so that's why we also try to build a web and mobile application to provide the accessible user interface for interacting with data and ecosystem model. So on the right hand side, you could also see the data flow. All the sensor here, actually it's been collecting the raw data, and the on-ground sensor going to the web storage system, or for satellite we have going to the Earth observation data cube. But all of that will go into our in-house, we call that EASY, Earth Analytics Science and Innovations Platform. That house it will put up all the data analytics hub and all the model ecosystem where it's running. And one thing about that is they run that in Jupyter environment or in Python. And the code that I talked earlier, the CFD code, it need to run on that environment as well. So a little bit about the model. You don't need to understand all of this slide. It is a lot of information here, but just seeing that we want to monitor a lot of water quality parameter. So you have temperature, you have all the turbidity, you have chlorophyll, you also have the algae and all the cyanobacteria or oxygen, all of that parameter in your water. And you could do that by using a bit of combination between physics or hydrodynamic, where you're tracking the flow, the temperature, and the physics parameter. And then you combine that with something it called the GROW model. So that is the biological model where you try to get the population concentration and all of that for the algae or the cyanobacteria or the biology. And you could also have a component of ecological and chemical in there as well. But in this model alone, I try to combine between hydrodynamic and GROW model. And then of course, the output here is why we put the output at the temperature and cell count, and then put that on our aquatic web service for people for end user to use. And you can see that this one has a lot of driving input, whether it's meteorology, of course, because you see that it depends on the meteorological input, the rain, the temperature, the air temperature, wind, all of that thing. It also depends on the biological input, because you know that the algae it grow in different temperature. So the optimum temperature, something in Australia here, a lot of algae resistant to temperature up to 30, 32 degrees. All of that thing you need to put in there. So you see that there's a lot of input. And how could we describe all of those things in mathematics? So we write a bunch. You also don't need to worry about those equation, but just seeing that those equation is a lot of ODE and PDE equation, so partial differential equation. So we try to build that governing equation to describe the physics and biological behind that. For example, here you have all the physics. If you still remember, it is the balancing of mass balance, energy balance, and momentum balance, and all that thing, and you put that in there. So try to describe all the physics in that leg, whether you have the short wave radiation, you have the wave inside the wind, all of that thing. And also for biology as well, you try to see that whether that the algae actually depend on the light, the temperature, and all that thing. So a lot of equation, right? So how could you solve all of those equation? Though it called CFD, Computational Fluid Dynamics. How could you solve all those equations using a computer? So to do that, here is the workflow for a CFD workflow. So you can see that all of the PDE equation could solving using the discretization method. It means that you created a mesh or a geometry, and then from there you created a lot of grid, and then each of that grid you put the physics setting or the solver in there, and you can see that pushing through all of that equation into each of the cells. So imagine each of the cell is like a cube, and you remember all the balancing equation. So something going out, something going in, and then going out, you keep that balance equation, and you solve that. But the thing is that to solve all of this equation with this grid cell, and then going into the full domain grid, and then put out at at a kind of beautiful simulation animation running here. Sometimes it running into the problem of computational cost. But for example, it just only did it from my PhD works that want to take 600 million cells to actually run just very small simulation like that. And to do that, you need to run your code in a compiling language. And why a lot of people back then use Fortran, C or C++. And the reason is the compile language, like C++ or C, it could translate directly into an optimized machine code. So you have the minimal runtime and you have a faster execution. Also, your memory control, you have a lot of memory allocation when you run your CFD. And also, you know that Fortran and C++, they have an array structure where you could have ideal for putting the grid for the PDE solver. Another thing is the loop and the parallelism. So you want to run that, solving that on a parallel computing or using the hard PC support. And lastly is it's been back there for a very long time. So Fortran already back there from 1950s. A lot of people wrote the code running that, and it worked perfectly. And for example, if you going to the Bureau Metrology right now and apply for a job, probably they will ask you whether that you know Fortran, because they're still using that code base for their model. And let's say that because all of that weather model or CFD, they run on a huge chunk of solving a lot of physics here and a lot of grid size like that. So why Python is relevant here? It's not because that the environment I told before it run on Python, and so it forced myself to use Python, but it's because Python, of course, at first you can see that in JIT conference it had a very strong community base. So that community also bring up a very active library, and also Python it's easy to it's high level, so it's easy to actually for someone to learn and then working scripting and then prototyping. But there's a lot of library out there for pre and post processing and also using machine learning as well. Python also had their own problem. For example, that it's well known that it's slow for running HPC or MPI interface. So a bit of comparison between Fortran, C, C++, and Python alone like that, you can see. And how could we actually take that code, I mean, it's the legacy, and then still use in the Python environment? And one thing is we could use the wrapper or glue to call the API from Python. So we use that C plus C or C++, let's say that it's hard. And we want to stay within the Python ecosystem. So we prefer to exploit the performance advantages of C or C++, but keep the usability of Python. So we do it by creating a kind of wrapper, so that wrap and hide the Python, the C++ code, and then we use the Python API function. It calls the code under math, and of course it makes our life easier when it works like that. So you can see that the magic happen is in how the parameter are passes from Python land to the C land, and then how the C and C++ code is action, and how the C and C++ objects are converted back into Python objective and passed back to the user. So you can see in the top image here, you have the Python API. It's calling the background of the mod CFD model. And then you have the API that calling, creating an API with high-level function, a code block. That is one way that we could actually using Python wrapper and glue to call and getting the CFD code to run. So here is one example of the Jupyter notebook that we wrote for that CFD code. You can see that it just simply typing sim.executive simulation, and then it just magically calling the CFD code and run and put out the temperature profile in there. So we're not done with that yet, because it just simply wrapping and then calling from APIs and then running that. So it's just one step to modernizing the code. Another step is that we understand that when we work with CFD, like I said before, you can see all the equation and the model. It needs a lot of input. It means that you need to calibrate it, and it's hard to do it manually. The reason is why we're doing that manually is that a lot of that code actually it not has the building hyper-tuning parameter function for you to calibrate it. And how we normally, or how I normally doing it, is that you know that the parameter there, you can see at the right there, it has, top left, it depends on the wind, the turbulence, the meteorological scaling, a lot of parameter. How could I normally do that? So I use my physics knowledge, and then I make the guess. So for example, I want to model a lake, and then I know that the lake is shallow. I know that the lake is like polymimetic, so limnological characteristic of that lake. And then I make that guess, whether that how much light going in, and then how the wind affects the lake and all that, and then I put that parameter in, and then I do the trial and errors. And sometimes if you have a good guess, then and you also need a lot of expertise, then normally it take me for one lake. For now for my model it take me about 2 weeks for perfectly tune the parameter. It got a lot of time. And one more problem, only me could do it. It's like you need a background and you need to have a lot of experience like that, and you want to transfer that to a broader team. No one could actually make that initial guess but me. And also after rise and repeat hundreds of times, sometimes it also didn't work really well. So you want that trial error to search in parallel, and you want to search at scale. You want to search the whole n dimension of parameter. And you also want it to run automate. And also you want it to just search to be smart and direct toward a global optima. But also we don't want a lot of coding here. So we want as little code as possible. And we found a way. It's a Python packet. It's called Optuna. So what is Optuna? So Optuna is the open source framework for automated hyperparameter optimization. So it's built for machine learning, deep learning, and general optimization, and then it has the best configuration with minimal manual tuning. We choose Optuna because you can see all that Python packet for parameter tuning in there, and then we compare all of them. We saw that it has flexibility and usability with the balance of all of that. And it also have a greater minimal code effort. So you can see in the right there, it's just simply you put all of your physics there, and then you put the range of parameter, and then just choose the sampler that you want, and then click and then it run. And then it run, you just choose the number of trial, and then it run. And between up to now, that also have a lot of sampler. And for our problem alone for the CFD modeling, we find out that the CMA-ES sampler, so it's based on covariant matrix adaptation and evolution strategy. We found that it actually works for complex, multivariate, continuous and high-dimensional and nonlinear and noisy optimization problem. Of course, having said that, it is trivial to plug in another sampler if you want to try it out later on. How it actually show out? So this is the result from two lakes. This one is Lake Hume. If you know it in Albury, it's southern of New South Wales, and up there it Graham Town Dam. So it in the Hunter region, like up to near Newcastle in up New South Wales. You can see that for when I doing that manually, and then for 2 weeks, and I was really proud of that. And then when we use Optuna, and you can see that it improved a lot on globally. And you can see that it fill in the gap between simulation and sampling. So we now not only done that, taking the CFD code and wrap it, we also trying to use Python packet at Optuna to turn manually hypertuning to kind of a automatic run and using Python. And so want to close it up with this slide. So from an advanced data analytics system perspective, it would be nice to have a breadth across from the CFD code, and then the wrapper, and then the Docker, and the Jupyter Hub. And then it would be much appreciated if we have, for example, if we have a partner that using the advanced data analytics system container, and so they could rapidly access the CFD if we make the launch profile available. So, and we also could hope to publish that that code for our tuning code in PyPy and Conda. So we actually solving a long-standing challenge in software. So we have a distribution through many layers of infrastructure and abstraction to a point that you can visit a website, import a packet, and tie the sim executive command to invoke the CFD code behind. My last slide is the partnership opportunity in AquaWatch. So we're not just only building the data hub, we also have a lot of pilot. We have an on-ground developing sensor. We work with NASA to actually develop the sensor on their satellite. And then a lot of Earth observation opportunity. So please tune in if you see that any of the partnership opportunity work for you. And for that, I thank you for listening, and my contact and email there.
Thank you very much. That was very interesting. Firstly, I've got a speaker mic for you as a present.
Thank you.
Feel free to grab that.
Thank you.
Now we've got time for a couple of questions. So if anyone has a question, please raise your hand. We've got a mic going around somewhere. Yeah, Mike's coming. Give us a second.
Thank you very much. It's really good to see like real math and machine learning algorithm. So all the time we talk about LLM. But my question will be about LLM. If you guys use LLM, for example, to write code, did you notice like which language you think LLMs knows better? And second question is, for this use case, do you think LLM can be useful at all? Thank you.
Um,
When I say LLM, I mean like ChatGPT and friends.
what is your first question is when we write code?
Yes, like if you guys use something like ChatGPT to help you out code,
Oh, yep. Yeah.
like which one do you think like knows better?
Yeah, so I've got Vive coding it getting more popular now, and one thing it also helped me myself personally as well when I try to actually build that wrapper. So we also try to use that Vive coding the GPT model to actually help me with building that wrapper and code. And actually AI, they could actually search through a lot of space and find to you even that hypertuning. It also suggests to you that what is the best hypertuning packet that could actually use for the purpose for the model. And one more thing is you can see that model has a lot of parameter, and one more advantage of using AI is it could actually help you to find the best, not hypertuning, but also data filling and data imputation to help you to clean up the data before putting into forcing that into the model to run the code. So there are a lot of usability when it comes to AI.
I think there's
That
one more question.
answer your question?
Yes, thank you.
Yeah, thanks.
I'll ask a bit about the modeling which you're doing.
Sorry.
I'll ask a bit about the modeling you're doing. Now you talked about using your experience in terms of giving the parameters and everything, right? And you used Optuna to basically do the optimization of the parameters. Now one of the things which brings to me to mind the basic concept of Bayesian models which I use, which basically use the inputs from the expert. Have you tried out those kind of models for your optimization? Because I can see a very good example of using Bayesian networks or something to further optimize your models. Yeah.
One thing when we use Optuna is sometimes, for example, I want to tune from the sensor data, so a lot of physics, and then turn into the data, for example, the AGI data. And in between that inversion, you need a hypertuning. But sometimes the hypertuning could give you a wrong physics. So sometimes you see that, okay, AGI, but why it very active in a wrong wavelength? You cannot explain that. Then that's why you need the expert involved. You actually need between both of them. It's just like when you train a model, and you need an expert annotation as well. So it's not just alone, but at least using it, you save a lot of time. Let's say that you don't want to run in one lake or one river. In Australia, you have a few hundred. And all of them, when come to environment problem, data is scarce. You're not, so you want to actually get machine learning to help you with scale it up. However, you want to get the physics also intact as well. You don't want that to happen. But like I say, Optuna still have. Instead of getting one leg and one expertise, you need to pay for that expert working for 2 weeks to tune that one leg. You could get the Optuna to do that first for you and get an expert to check for the whole range of legs. So that to it already, you could see the advantages of using that hypertuning or some deep learning search for hypertuning.
Thank you.
All right. Thanks a lot. That was a really great talk. I really enjoyed it.
Thank you,
We've
Kai.
now got a 10-minute break until our next talk, and then we'll be back. Thank you.
Thank you.